Hi, everybody. It's nice to see you again. It's been a few months, and we're back with a second edition of our videos on a gentle introduction to conformal prediction and distribution-free uncertainty quantification. I'm Anastasios.
I'm Steven.
Yeah, and it's nice to be back in person with Steven again to film these videos, and we can be together.
So today we're going to talk a little bit about advanced aspects of conformal prediction. I'll remind you, last time we talked about the basic algorithm. So it's a conformal prediction here is a way of getting finite sample confidence intervals with any machine learning model and any data set. And you get this rigorous statistical guarantee that makes it really attractive and really important to use in practice.
Today we're going to talk about a slightly more nuanced topic, but nonetheless a really important topic that has to do with conformal prediction, and that is the difference between marginal and conditional coverage. So as you can see on these little plots, the marginal guarantee that conformal gives you doesn't ensure that you're making errors in an equalized way across your space. Sometimes you want to make sure that no matter what data point you give me, I still have 90% coverage. This is the type of topic that we're going to be discussing today. Even if we can't get it entirely, how do we approximate it and so on. And in addition, we're going to be talking about evaluating conformal, the effective and efficient diagnostics that you need to tell if your algorithm is working.
So a quick recap into the basic conformal algorithm before we dive into these details. So recall that our goal was to make these confidence intervals or prediction sets in our language, these T of X confidence sets, such that the probability that a new data point the new response for the new data point falls into my confidence set is at least 1 minus alpha. You can think of 1 minus alpha as 90%. So I have a 90% confidence interval for all of my predictions. The way it works here is you start off with some heuristic notion of uncertainty. So you take your machine learning model and you extract some information about uncertainty from it. And in particular, you extract that in a score function here that we call S of xy. The score function is the most important part of conformal prediction. It's the design choice that is going to determine a lot of the advanced properties that we're going to talk about today. So figuring out the right score function is going to be an important thing, and we've given you some good options for that, and we're going to explain why they're good options in more detail as we go today. Once you have that score function, the conformal procedure kind of tunes a parameter of that score function in order to give you this 90% coverage. So in particular, you're going to compute this quantile according to the conformal recipe, and then you're going to deploy these prediction sets that are all y's such that the score falls below some value. So this is how I get my confidence sets, and remember, I promised you that they have at least 1 minus alpha coverage, 90% coverage, no matter what the distribution of the data is and no matter what score function you started with. So again, this is the guarantee we get for any distribution. For any number of data points, we get 1 minus alpha coverage. And this is a really strong sort of safety net for any machine learning model. You can now deploy it with a lot of confidence because I'm still on average going to get 90% coverage. However, it's not a perfect property. And in particular, this contract here that I give you at least 90% coverage across new data points doesn't rule out the possibility that I could be making all of the errors in one part of the space. So for example, I could be making all of my errors here in the red part of the space and kind of never making errors here in the green part of the space. Okay. So we're going to talk about this precisely with some kind of rigorous math. The terminology we're going to use is marginal versus conditional coverage. So conformal prediction here, this property, is marginal coverage. So I can promise you always have marginal coverage. Often we would want to get something even stronger, this conditional coverage, and we'll talk about how you can and cannot, how you can try to get close to that, and how you can tell how close to that you are. So to explain conditional coverage a little bit more, to get a feel for what it means, consider this example where we have two groups, okay, group 1 and group 2, and then the green dots here are going to represent data points where my intervals did cover correctly, and the red points are going to represent data points where I miscovered. Okay? So if I did not have any coverage at all, I would maybe have 50% miscoverage points, maybe even more in group 2. Okay, so if I had no coverage, I could just have some large number of miscoverage points. Conformal puts me at least in this center column where I have marginal coverage. Marginal coverage means that on average, I have 90% coverage. So if you look here, in the top, in group 1, I have a lot of coverage. In the bottom, I have a little bit less coverage, say 90%, or say 80% in the bottom, and 100% on the top. And so on average, I have 90% coverage. So conformal says I'm at least in this center column, and I'm not in the leftmost column. Now, in contrast, what you might prefer is to be in the right column, which is conditional coverage. So conditional coverage means, say, split across these two groups in the data, group 1 and group 2, I have 90% on the top and 90% on the bottom. So this is the ideal setting we would like to be in this world, and we're going to talk about how close we can come to achieving this balanced coverage. As another example of conditional versus marginal coverage, we can think of a regression example where there's one continuous feature, X. If I had no coverage, again in the left, I maybe have intervals, prediction sets that are too narrow here. They don't contain 90% of the data. Conformal guarantees that I'm at least in the center column where on average these bands, these yellow bands, now contain 90% of the data. I would like in a perfect world to be in the right column where the bands contain 90% of the data and they also do it in kind of a balanced way. So in the harder region of space here on the left, they're wider, and in the narrower region of space in the middle, they're narrower. Okay? In the easier region, they're narrower. So again, we can't guarantee that this is going to happen with conformal, but there are best practices that will usually put us over here. Okay. So formally, using our probabilistic language, conditional coverage is the following property. The probability that I cover a new data point, that y is in t of x, conditional on x equals x, so for any fixed feature vector x, is at least 1 minus alpha. It's at least 90%. Okay? Conformal does not guarantee this, as we've said a few times, but you can usually get pretty close when you use the techniques that we've talked about in the first video of the gentle intro. Okay, so we can often get close to this. Again, the difference here is now I'm conditioning on x equals x, so I'm promising you that everywhere in the feature space I have 90% coverage, and we can often get very close to that. Today we're going to show you how to get close to that and how to test it very precisely, how to check that you're getting close to this. So as an example, consider classification. If we knew the probability of y equals little y, the probability that y is some class, given x equals x, what would we do to get conditional coverage? Well, what we would do is we would go down the list of classes from most likely to least likely, and we would stop when we hit 90% mass. So let's say that 1, 2, and 3 here add up to 90%. My prediction set would be classes 1, 2, and 3. So if we had this perfect knowledge of the probability that y equals little y, given x equals x, this is what we would do. So what APS, the method from the first video, does is we plug in an estimate for this quantity. So we plug in a model for P of y equals y given x equals x, and the closer that model is to the true distribution, the closer we are to approximating conditional coverage. So in practice with APS, you can get very close to conditional coverage depending on how well or poorly your model is doing. So next up, we're going to talk in more detail about how to evaluate conformal prediction, and I'm going to hand this off to Anastasios.
Okay, I'm back. So Stephen just told you about a method that, if you use it properly, brings you somewhere close to conditional coverage, right? But you don't really know how close you are until you perform some evaluations. And indeed, you've implemented conformal prediction, and oftentimes, if you're like me, you write your code, and then you're really worried that there's a bug, right? So there's plenty of issues that can come up in practice that have to do with whether you've implemented conformal properly and also whether your conformal procedure is any good. And we're going to talk about them now. In particular, we're going to talk about 3 evaluations, or 3 sort of genres of evaluations. The first is evaluating coverage. So this is just debugging. It turns out that coverage is a random quantity. It depends on your data. So it depends on your sampled calibration set and also your validation set. But somewhat surprisingly, it has a known distribution. So you know the distribution of coverage a priori, and you can write it down parametrically. It's a beta distribution. And for that reason, we can evaluate coverage and then tell you pretty much precisely what that number should be. over many different splits of your calibration data set. So we'll tell you about that. We'll also tell you about evaluating set size and adaptiveness. So these are more properties of your procedure and data set. You usually want your conformal procedure to produce small sets. We talked about that in the first video. And there's some warning signs that happen if, for example, your set size degenerates to a point mass. If you have fixed size sets always, it might mean that your score function is not very good because you don't have good dynamic range. And also adaptiveness. So we're going to talk a little bit about basically trying to evaluate approximations of conditional coverage or things that are implied by conditional coverage, just to sort of get many views on the topic to see how adaptive our methods are, how close to conditioning we are in our problem setting. So for example, I've drawn here group 1, group 2. You might look at the coverage within group 1 and group 2, and if it's really different, you might say, well, there's a problem. Maybe I need to account for that in my score function. Okay, and we'll learn how to do this all pretty efficiently. So if you're using something like a deep learning model, you don't need to run it 100,000 times in order to understand the distributions of these quantities. Okay? So first, let's talk about coverage. As I said, the distribution of coverage is known in advance. So we know it exactly. The only thing that we need is n, the number of data points in your calibration set. And so for that reason, when you evaluate coverage, it's a really useful bug check. Basically, if you don't have coverage that's sufficiently close to, let's say, 90%, and you have 2,000 data points, if it's outside of like 90% plus or minus 0.1 in that case, you kind of know that you have a problem. So in particular, we can write down the distribution of coverage this way. It's a beta distribution with these parameters L, n minus L plus 1, where L is this basically the conformal quantile, like the index of the score that we chose. And you can look at the gentle intro for more fine-grained explanations of why this is the case. But the bottom line is that depending on the size of your calibration set, the variability of your coverage is going to change. So in particular, if I run conformal once, I'm not guaranteed that the number that actually comes out of the conformal procedure is going to give me 90% coverage. So it's only 90% coverage on average. If I were to repeat this infinitely many times, it would be 90%. Or, at least greater than or equal to 90%. And there's also that matching upper bound. But the fewer data points you have, the higher the variability of that is. Right? So if you have 100 data points, it should be sort of roughly looking like this. It should have sort of a 5% spread. And if you have 2,000, 3,000 data points, it's more of a 1% or 0.1% spread. And we actually have a table of these numbers in the written version of the gentle intro that you can cross-reference that'll tell you precisely sort of the bounds within which your coverage should be when you run conformal. So, basically what you should be doing is when you implement your conformal procedure on your computer, what you're going to do is you're going to randomly split your data, right? So in this step, you're going to resample your data. You're going to have a calibration data set and a validation data set. And then you're going to use the calibration data set to calculate Q hat, which is your conformal quantile, that n plus 1 minus alpha ceiling over n thing that we talked about in the last video. And then on the validation set, you're going to calculate coverage. All right, so you're just going to look at each data point inside your validation set. You're going to create the prediction set using your Q hat that you got from the calibration points. And then you're going to take the average of whether the point was included in the set. That's called your empirical coverage. So that's within this for loop. And you're going to do this t times. Okay, so big T is the sort of the number of trials, which you want to be large so that you can get a good estimate of how close you are to covering. So doing this procedure many times should create a histogram that looks something like this. So if this is the theoretical curve that you would derive by plotting this beta distribution, your empirical curve should look roughly like the theoretical curve, maybe slightly wider due to the if you have a small number of trials. So plotting this histogram is one of the first things that Steve and I have done in the papers that we've written on conformal. This is like step one. Evaluate coverage, make sure my procedure is not actually wrong. Because if it is, you have a problem and there's no point doing anything else. But okay, so now let's imagine we've passed step one. We know the histogram of our coverage roughly looks like the theoretical one. So now we're pretty sure we're doing the right thing. What are the properties of my procedure now? So usually, again, the first property of interest is the set size. You just kind of want to look at the marginal distribution of the set size, okay? And as we said in the first video, smaller sets are usually a bit more useful, right? Small is generally better. And the reason for that is because, you can always achieve coverage by having an enormous prediction set that takes up the entire label space. So usually you want something that gives you more fine-grained information about your prediction. Generally, that means you're small. So a lot of times when you run a conformal procedure that looks good, you get set sizes that look like this. It's sort of like, mostly they're small, and then there's a few hard examples. Of course, this will depend on the distribution of your data. Maybe all of your examples are the same difficulty, in which case, the right-hand side where you have a sort of a point mass at a particular set size, maybe that thing is reasonable, but usually that's not the case. Usually what happens is your data set will have some spread, and like X will give you some signal about how hard it is to predict Y. And that's actually the case where this can be a warning sign. This can be basically a warning sign that your score isn't giving you a good heuristic notion of uncertainty. It's not telling you about whether points are going to be easy or hard. And so your conformal prediction procedure is sort of regressing or collapsing to a trivial procedure that gives you fixed width intervals, which can be bad. And the way that you evaluate this is similar to the conformal evaluations that I discussed in the last slide. And I'll present an algorithm that goes into this procedure in more detail. But basically, you're doing random splits of your data, constructing prediction sets, and then evaluating their sizes. Okay, and the third evaluation that we're going to talk about is about adaptiveness and conditional coverage, right? So unfortunately, it's usually impossible to measure conditional coverage directly. And the reason for this is, if X, for example, is continuous, imagine that we're actually doing image classification. What does it even mean to be conditional on X? It's not clear that really exists, and even if it does, it's hard to evaluate because you're not observing repeated copies of X. You're sort of you have a few images, and the space of images is so large that you can't really hope to measure each part of it and then try to evaluate the coverage there. So instead, you need to kind of like take cuts around your space and try to look within those. You have sufficiently many data points within a particular stratum to understand what the coverage is in there. And by choosing those strata in an informed way, you can sort of get a look into how adaptive your procedure is and how sort of fair it is, basically, across those strata. So one example of this, one sort of proxy for conditional coverage, is label stratified coverage. So, it might be true if I'm classifying cats, dogs, and elephants that I don't want to make all my errors in the elephant class and get all my cats and dogs correct. Maybe I actually want 90% coverage for cats, dogs, and elephants. One trivial way to screw this up would be just to never include the class elephant in my prediction set. Maybe I can still get 90% coverage if cat and dog are sufficiently populous in my data set. But usually I don't want to do such things. I don't want to trade off errors in this way. It's sort of like against the philosophy of the sort of prediction intervals that we're trying to construct. So instead, what you do is you just stratify. So you look at each of your classes and you evaluate coverage within them. So that just looks like, I just, separate my data points into bins. I have my cats, my dogs, and my elephants. And then I take the average fraction of the time that the label is included in the prediction set over my validation data. And you kind of want those to be even. If those bars are even, it means you're getting close to conditional coverage in Y in the classification setting. Now, when you have like well-named strata, like in classification, or if you have some, other variables at play, if you're trying to stratify things by like socially meaningful factors like race or sex, maybe, this strategy is going to work, but oftentimes you don't have that. Oftentimes you kind of just need a problem agnostic way of measuring how adaptive you are. And one way of doing that is just by stratifying by the size of your prediction set. So, if you think that small prediction sets correspond to easy examples and large prediction sets correspond to harder examples, then the way that you interpret this is, among my small sets, among my sort of easier examples, I have coverage. And also among my large sets, among my hard examples, I have coverage. Now, this is often a desirable quality because what you don't want is a procedure that gives up on all hard things and then includes all easy things. So, make this very high and this very low. And the reason is because if you do that, then the large prediction sets are not actually meaningful anymore. They're not really guaranteeing that they contain the right label. And then that calls the whole procedure into question. So oftentimes you want to evaluate things like this just because they give you a better insight into your method. So let's put some notation on the board so that we can understand how to do this efficiently in code. Okay, so we're just going to lead you through this pretty quickly. But you have a model, so it's a classification model. It takes you from the space of your x's, your input data, you can think about this as images, to the k-simplex. The k-simplex is just softmax distribution over my classes. And you just think about this as a pre-trained model, as it was before in the last video. And then you have this data set. The data set includes basically n calibration points and n val validation points. Okay, so you have your calibration and your validation set, but we put them all in one big list. Okay, now step 0 of this is you're going to cache the matrix D here. So what I've done with D is I've taken f hat, and I've run every data point in my data set through f hat. And what I got is a vector. This is like the softmax vector in the classification case. And I did this for every data point. So now I've concatenated them vertically. And now I have a matrix. And after I have this matrix, I never run my model again. The good part about this is that now after computing D and storing it, you no longer need your big GPU cluster to run your transformer model to understand whether your conformal procedure, which is pretty lightweight, doesn't actually require such heavy-duty machinery, to understand whether your conformal procedure works. Now you can run your conformal procedure 1,000 times to try and evaluate coverage. You don't need to worry about, the speed it takes to run your model or whether or not, you can fit it on your GPU. So let's just take a really detailed look at this. This will be the last thing that we look at today. An algorithm for evaluating conformal with these cached outputs. So the question now is, once we have D, what do we do? So the basic philosophy is just as we explained on that evaluating coverage slide. We're just going to split our data set, run conformal, and then calculate our metrics. So here I've instantiated lists, 3 lists, one for each metric. This will be our coverage, this will be our sizes, and this will be our, I guess in this case, it will be our label stratified coverage. So this will be one measure of adaptiveness. Now, you can have many lists here. And one of the benefits of the algorithm that I'm showing you is that you can basically plug in any metric that you want into this general pipeline and use that to evaluate your procedure. Okay, but I'll just show these 3 for now. So this is our for loop over our trials. You want T to be as large as you can. This will fill out your histograms. The first thing you do is you shuffle and split your data. So you randomly permute both D and Y, where Y is the vector of class labels. And then you get these 4 things here, the calibration data set, the validation data set, these are your model outputs, and then your calibration Ys and your validation Ys. Now, here is the step where you're calculating your conformal score. In this case, we're using not the APS score that we showed before, but a different classification score just for convenience. And then you calculate the conformal quantile of it. So this is just the regular conformal machinery that we're running through here. So you calculate your scores, you calculate your quantile, and then you can form your prediction sets, okay? And in this case, we're forming prediction sets on the validation set here. So this is dval. Then we look at which data points in our validation set are covered. So in particular, this covered variable here, this covered variable is a vector that looks like this. It's filled with 0s and 1s, and it's the length of nval. All right, so we just looked at each of our prediction sets, saw whether it covered the correct answer. And now we can compute whatever metrics we want and then store them in our lists. So the first thing we do is we evaluate coverage. So we look at which points are covered, and we take the mean of this binary vector. And that mean is the fraction of points that are covered. And then we add it to our list. So that goes in here. Then the second thing is our sizes. So our size metric is just, we we sum the sets along axis 1. This is more of a Pythonic thing, but you just evaluate the set size and then you plug it in to this list here. You append it. And then the last thing we do is we calculate our stratified coverage. Okay, so this is a little bit more of a detailed line, but we index the prediction sets that cover the true answer. So we index our covered vector here by each class. So we do this stratification. And then we calculate the coverage just like we did in this line for each class in our data set, for each of the K classes. So this will give us a list. It'll give us a list that's the same length as the number of classes that we have in our data set. And we'll append that list to stratified. So now stratified will be a list of lists. And you can average that, along the number of trials. That'll give you sort of your size or your label stratified coverage, an approximation of that. Okay? And so we did all this, and we only needed to run the model once. That was the benefit. We didn't need to run our neural network T times on our data set. We just needed to do it once, and then we used our cached data to compute all of the metrics that we desire and more. So, you can add your own line 11, 12, 13, 14 that are whatever metrics you desire. Okay, so that's it for this video. And next time we're going to be talking about distribution-free uncertainty quantification beyond classification and regression. So in the, community of machine learning writ large, a lot of times you have problems that don't naturally lend themselves to conformal prediction. Problems with more sophisticated notions of error rates and more complicated structure that you need a bigger toolbox to address.
So we're going to introduce an extension of conformal that's going to allow you to control many such error rates for different learning problems. For example, we're going to talk about segmentation problems where in a particular image, there's going to be some region of interest that you're trying to detect. In this example, it is tumor images, and you're trying to find the set of pixels corresponding to tumors. We're going to return confidence sets that contain that region, and in particular, we're going to promise you that those sets contain 90% of the true tumor pixels. So this is the false negative rate. It's one example of a statistical error rate for the segmentation problem that you care about in practice.
We're also going to introduce a way of doing out-of-distribution detection plus outputting prediction sets that achieve coverage. So, as you can see here, we've drawn a squirrel from ImageNet that has a hat on it with a feather. This squirrel's out of distribution, so sometimes you want to know that. Sometimes you want to know that, and then you'll output a prediction set that is empty to signal, hey, this guy is not from ImageNet. But then within the ones that are deemed to be from ImageNet, we're going to give you a prediction set that has coverage. And so we'll be able to do both of these tasks rigorously. So there's two error rates at play here. It's not just one. Two error rates. One of them is the false positive rate of the out-of-distribution detector, and the other one is the coverage of these prediction sets. We'll be able to actually control both using the same technique jointly. And that it doesn't stop here. There's a wide array of machine learning problems that you can apply basically the same philosophy to, including, for example, instance segmentation and object detection. And we're excited to share those with you in the next video. So see you soon.
See you soon.